Now, maybe what you might be thinking about is at some point, like if we think about this muscle, okay, maybe what might be coming to mind is maybe there's a part of this muscle that's not functioning properly, and what's happened is inside where we're going to have it, and it could even be coming from the large nerve that enters into this muscle, okay, and it's usually what happens is at that area for those terminal buds, the nerve has died. And if that's the case, that one cell is not functioning. Now, if it was just one cell, probably don't even notice it. But let's say it begins to be 2 or 4 or 6 or 8, you know, depending on the amount of fibers that are in here. If you get enough of them that the nerve doesn't communicate anymore with that fiber, part of that muscle is going to be affected. Does that make sense? So when we end up with this situation, okay, this area that's being created, this neuromuscular junction, that is going to be the reason that the fiber, the cell, is going to do its job. The job of that cell: contract, relax. So, this means we're going to be dependent on a neurotransmitter. That gets fun. So what is it that once we have that fiber, that cell, and it has its connection to that nerve, okay, that terminal bud of the nerve, okay, we're going to see that the structure that we find for that one cell plays an important part on how the entire muscle is going to react. Now, if you send an impulse to the one fiber, it doesn't mean that by just exciting one fiber, the muscle is going to contract. That's not what it means. Okay? We need quite a few of those fibers to be excited for that entire muscle to contract. So the structure that we find, we're going to see that if we look inside the muscle cell, the muscle cell is going to have some overlapping that's going to be present. All right? We're going to have what's called myofibrils. We're going to have one of them that's thick, and several of them around the thick one that are going to be termed thin. And these are going to be myofibrils. Now, inside that muscle cell, okay, let's think about having this long fiber making up that cell. We term the fluid sarcoplasm as cytoplasm, okay? Sarco is once again going to refer to muscle because we're going to be looking at what's termed a sarcomere.
Aren't there these things called like Z-lines?
Yes. We're going to find that these, when we have the distance, because this one sarcomere, that banding that shows up, it's giving a defined distance. And it's defined by the bands on each end known as those Z discs or the Z lines. All right? We'll have the thin, we'll have the thick. So we're looking at myosin and actin. And actin is going to be attached to the Z disc. Looks like myosin is just simply floating in the middle. It's not. But that's sort of how it looks. The thick and the thin. I need them to do this number. Okay? A sarcomere. If I were to continue down, let's say I had more of my board, okay, and I were to continue drawing my fiber, all right, I would have sarcomere after sarcomere after sarcomere after sarcomere after sarcomere. So the entire length of that fiber would be a sarcomere after sarcomere after sarcomere. And somewhere on that fiber is going to be the connection, my neuromuscular junction. Is everybody with me so far? Okay? So if I break it down, if I look at my muscle as a whole, begin to break it down into a group of the fibers, get a fiber, have my banding, and break it down into sarcomere, 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 and pull and look at only one of those sarcomeres. This is what it's going to look like. I'm going to have my thick filament surrounded by thin, and note that I have several of them in a sarcomere. So the thick one surrounded by thin, I would have another thick one surrounded by thin, thick surrounded by thin, thick surrounded. Does everybody see how I'm getting that? Okay? And if I take a peek at only one of the connections between a thick and a thin, this is how muscle will contract. This is the point we have to be at to understand muscle contraction. So, Z disc to Z disc, one sarcomere. I've got my thin filament attached to that Z disc. As you can see, I've got some little springy stuff that's present. What do you think that springy stuff's going to help with? I got to have the ability for it to do this number and then back out. So that tells me that these thin filaments, okay, they need to pull towards the M line, middle. Is everybody with me? It's going to do this number. And then relax. Okay? Sounds pretty simple, right? No?
It sounds simple, but it's not.
It's not going to be. But here's my question. Okay, if we start to talk about the structure, the makeup, that it's at this point, okay, this one sarcomere from Z disc to Z disc, and we got to go, okay, everything about muscle contraction is going to be based on all of those sarcomeres with all of those thick and the thin that are lined up down that entire length of that muscle fiber, that muscle cell. And then not only do I have to make sure that that fiber does it, I got to make sure the other fibers around it do it, and then eventually all the fibers of that one muscle. Why is it going to be so important for me to understand it at this level? Because this is going to be the smallest unit of this cell, this fiber. It is the working unit of the muscle. Sarcomere, it is the functional unit of the muscle fiber. If it is not functioning, what's going to happen to everything else? It is not going to function. But wait a minute. What's going to make it function? Everything that we have learned in class goes back to my sodium, my potassium. Now we're going to see the importance of calcium. If your calcium levels in your body are wrong, your muscles are going to have a problem. Not just bone in your body, your muscles are going to have a problem. And therefore, it becomes clinically significant. And therefore, it becomes important to understand how to read lab reports and understand the ramifications of the numbers you see. So, the structure that we're going to see for the actin and the myosin, I got to point out some things to you, okay? And it's actually pretty interesting what happens. So if I begin to take a peek at the structure of my thin filament, my actin, okay, note that it looks like these globes that are present. The globes have these little dips or dents in them. Okay, so everybody kind of see that? And then it looks like it's wrapped in a double helix. So the structure of my thin filament, I'm going to find that I'm going to see these little actin molecules, my globes, and then this line that looks like it's forming a double helix, this is termed tropomyosin, and at each bend, at each curve, there is some troponin. Now, these little dents, these little pits that are in my globes, look what they have. They have an active site. So, it's going to make things kind of interesting. Now, if I look at my myosin, the thick filament, it just looks like golf clubs to me. Okay? Looks like you just take a whole bunch of golf clubs and just lay them down. And what we end up with, we're going to have what's termed these myosin heads. Now note the way that they look. It looks like we've got this really cool twisting, these heavy chains, and therefore at the end we end up getting the two myosin heads. What do they look like they could fit into on my thin filament? The active site. Oh! And my structure is showing me that I've got this thick filament with these myosin heads that can pop up and fit into an active site on the globes of my fin. Which way did I say this structure needed to move? I got to make it do this number for muscle contraction. So, do you think maybe the myosin head is going to be able to attach to an active site? But do you think it's going to be very easy for it to do it? No. But the way it does it, yeah, really cool. Trust me on that. So, take a break. Be back at 12:30.